Introduction to Sequences. Objectives. By the end of this lesson, you should be able to define a sequence, use sequence notation and terminology, find the general term given a sequence, and understand when a sequence converges or diverges. Alright, so let's start by informally defining a sequence. A sequence is just a list of numbers where the numbers are indexed by a variable. So now let's take a look at the notation. So here we have this expanded out list of numbers. A1 is some number, A2, A3, A4, and they're all separated here by commas. And these dots at the end, this ellipses, just means that this list goes on forever. So instead of writing this out every time, the shorthand notation would be to write A sub n, so n is the indexing variable, inside of these curly braces. So that implies that this list of numbers is the same as this written out list of numbers here. And we can also choose to write out specifically where the index is going to start. So here, this subscript down at the bottom right side of the curly brace, n equals 0, means that 0 is instead going to be my starting index. So here this has a starting index of 1, but I could have made it a 0 if I wanted to. And then of course it's going to go on forever to infinity. So let's look at two examples with numbers now. So I have this first sequence, A sub n, and the list of numbers in A sub n is 2, 4, 6, 8, and so on and so on. And in this sequence B sub n, I have 3, negative 8, 0, negative 2, square root of 3, 1/2, and this 2 goes on forever. Now, taking a close look at B sub n, notice that the list of numbers can include negatives, we can have 0, we can have square roots or irrational numbers, we can have fractions. Really, a sequence is just a list of any numbers, and I tried to make it so that B sub n has no pattern associated with it, but it's still considered a sequence. But for our purposes, we're mainly going to deal with sequences that do have some recognizable pattern. So there's an obvious recognizable pattern in A sub n. To get from one number to the next, we have to add 2 every time. So when that occurs, when we can find a pattern, then we want to find a way to represent the general term so that we can find the 100th number in the sequence without having to compute all of the 99 numbers before it. So the general term for the sequence A sub n is given also by A sub n, but without the curly braces. So the general term A sub n, or the rule for finding the nth term in the sequence, in this case is 2 times n. So you'll notice that if I go ahead and let n equal 1 here, that if I substitute 1 into this n, 2 times 1 is 2. That gives me the first number in the sequence. If I substitute in 2 after that, then I get the next number in the sequence 4. If I substitute in 3, 3 times 2 is 6, etc. So this is the general term in the sequence. And then formally our index variable, that's n in this case, and it can officially start anywhere, but usually we start at 0 or 1. So in this top notation, we said that the index here indicated that the starting index was 0, but this sequence, this general term, implies that we're going to start our index at 1, because if I were to plug 0 into this n, I'd get 2 times 0 is 0, which is not the first term. So this general term implies that we have a starting index at 1. So now let's go ahead and take a look at the formal definition of a sequence. A sequence is really a function whose domain is either the positive or non-negative integers. So let's go ahead and think about the sequence that we just took a look at. So we had A sub n equals 2, 4, 6, 8, dot, dot, dot. And then what I'll go ahead and do is include the general term in the sequence, 2n, and it does go on and on forever. So the general term was given by A sub n, which was 2n. So the function notation that we're used to is something like f of x. So let's consider f of x equals 2x instead of 2n. So f of x equals 2x, if we were to graph this thing, 2x is a line that, goes through the origin, has a slope of 2. And we'd say the domain of f of x equals 2x is from negative infinity to infinity. I can plug in anything from negative infinity to infinity and get out a value on this line. So the domain here is all real numbers. So the difference is that in a sequence, the domain is the positive or non-negative integers. So that means that non-negative integers means that we could either start at 0, or positive integers means we can start at 1, and we're talking about the integers here, so no fractions, no rational numbers, 0, 1, 2, 3, 4, 5, etc. So in order to get the numbers in the sequence, we had to start by substituting in 1, starting with a positive integer, and then we had to substitute in 2, 3. So we're skipping all of the numbers between 1 and 2, and all the numbers between 2 and 3. Whereas the function f of x doesn't skip any of those values. I can substitute 1/2 into f of x equals 2x and get out the value of 1. So that's the real difference here, is that we're talking about only being able to substitute in values that are positive or non-negative integers. So a sub n can really be thought of as a of n, just like f of x, if we really wanted to. But instead of the parentheses notation that f of x sort of uses, like f parentheses x close parentheses, we actually use subscript notation when it comes to the general term of a sequence formally. And it's really to help distinguish that we aren't plugging in every possible number of the domain like we would in a typical function. Our domain is restricted to either starting at 0 or starting at 1, all of the integers from then on. Alright, in this first example, we're asked to write out the first 5 terms of the sequence a sub n equals negative 1 to the n over n squared. So at this point you might be thinking, well, what do I start with? Where's the starting index? If we assume the starting index is 0, we're actually going to have a problem. So we should be thinking either 0 or 1, but substituting 0 into the denominator for this n on the bottom will give us undefined. So we're actually going to have to start with an index of 1 in this case. So let's go ahead and start with a sub 1. So we're going to take the 1 and substitute it into every n. So the numerator is negative 1 to the 1 over 1 squared. So negative 1 to the 1 is negative 1 over 1 squared is 1. So a sub 1 is just negative 1. So now let's try a sub 2. So negative 1 squared, so I'm substituting the 2 into the n in the exponent, over 2 squared. So now the negative ends up going away because I'm squaring it, so the top is just positive 1 and the bottom is 4. So now let's try a sub 3. So I'm going to have negative 1 to the 3rd power over 3 squared. So 3 negatives multiplied together still give me a negative, and 3 squared is 9. And then a sub 4, so I'll have negative 1 to the 4th over 4 squared. So 4 negatives gives me a positive, and then 4 squared gives me 16. And then finally, a sub 5 is negative 1 to the 5th over 5 squared. And 5 copies of negative 1, an odd power of a negative number, is still going to give me negative 1 over 25. So if I wanted to write this out as a list of numbers, I'd start out with a sub 1, which was negative 1, a sub 2 was 1/4, then negative 1/9, 1 over 16, and negative 1 over 25, and this list does go on forever. So here are the first 5 terms of the sequence defined by a sub n equals negative 1 to the n over n squared. So for this example, what I want you to recognize is that negative 1 to the n made my terms alternate in sign. So I started out with a negative number, and then positive, negative, and that trend is going to continue due to this numerator, negative 1 to the n, that forces the sign to alternate. So now let's take a look at the next example. Write out the first 5 terms of the sequence a sub n equals 1 over n factorial. So the exclamation point, if you're not familiar with it in math, means factorial, and we'll go over what it does in a second. So on this problem, again, we would start out by trying to use 0 as the starting index. And you might think, well, if I substitute a 0 into this denominator, I'm going to get out 0. But this is one case in particular where that is not the case, because the definition of factorial says that 0 factorial actually equals 1. And this is strictly by definition. So when we go to find the first term in the sequence, a sub 0 is going to be our starting index, or 0. So 1 over 0 factorial is 1 over 1, which equals 1, so that's my first term. A sub 1 is going to be my second term, so 1 over 1 factorial. So let's just go over what factorial means. So in general, n factorial means that we're going to multiply by every integer less than n ending with 1. So n factorial is n times n minus 1 times n minus 2 dot dot dot, multiplying all the way down to 3 times 2 times 1. So we multiply by every integer from n all the way up until 1. So every integer less than n all the way down to 1. So 1 factorial would just be 1 times 1. So that's 1. So 1 over 1, I get 1 again. A sub 2, that's 1 over 2 factorial. So let's expand it. 1 over 2 times 1. So 2 factorial would just be 2, and then the only integer less than 2 is 1, and we don't go anywhere past 1, so we stop there. So this is 1 over 2. A sub 3 is 1 over 3 factorial. So this is 1 over 3 times 2 times 1. So 3 times 2 is 6, times 1 is still 6, so this is 1 over 6. And then a sub 4 is 1 over 4 factorial. So 1 over 4 times 3 times 2 times 1. So we already said 3 times 2 times 1 is 6, and 6 times 4 is 24, so this is 1 over 24. And we will be dealing a lot with factorials, and we rarely go any higher than 5 factorial. Which happens to be 120, so you'll just get used to knowing what those values are, and we really don't go higher than 5 factorial. So here, the first 5 terms of our sequence, even though notice we stopped at a sub 4, we are at the 5th term in the sequence. So listing them out, we have 1, 1, 1 half, 1 sixth, 1 over 24, and then this list will go on forever. Alright, in these next examples, we're going to go backwards. We're going to write an expression for the general term now given the sequence. So my sequence is 1, 2/3, 3/5, 4/7, etc. And whenever I have fractions, it would probably be easier to think about what's the pattern in the numerator and then what's the pattern in the denominator and how those relate to the indexing number. Well, 1 is really 1 over 1, so I can still think of the first term as a fraction. And because I'm deciding the general term, I can also decide the index. So in other words, 1 over 1 can be a sub 0 or a sub 1. And since they both have 1's involved, I'm going to go ahead and call the first term a sub 1, the second term a sub 2, a sub 3, a sub 4, etc. Alright, so now I'm in search of some sequence a sub n where I have to define the index. So the index is going to start at 1 and go on to infinity. So now I want to find a general way to express the nth term, any term. So if I wanted to find the 50th term, I can use this rule to find it. So let's focus on the numerator. So we said that we're going to go ahead and start by plugging in 1's everywhere, and then we're going to plug in every integer thereafter. So we're going to start with 1 and then plug in 2 and then plug in 3 and then plug in 4. So the numerator here is actually pretty easy. The numerator is going to have to be n. So if I start at 1, the first term is going to have a 1 in the numerator, and then the second term will have a 2, and then a 3, and then a 4, and so on. Now, in the denominator, I have 1 again, but now the second denominator is 3, and then 5, and then 7. So hopefully you recognize the pattern to be odd numbers. Now, to represent odd numbers in a generic way, we have 2 different options. So an odd number can be thought of as 2n plus 1 or 2n minus 1, where n is an integer. And so the reason for that is, let's think about substituting in some values for n into both of these. So if n equals 0, so if I substitute in 0 here, 0 times 2 is 0, plus 1 is 1. And then if I substitute in 1 next, 2 times 1 is 2, plus 1 is 3. If I substitute in 2 now, 2 times 2 is 4, plus 1 is 5. So I'm always going to get out the odd numbers from 2n plus 1. And then same thing for 2n minus 1. So if I substitute in 0, 2 times 0 is 0, minus 1 is negative 1. Negative 1 is an odd number. Now plug in 1. 2 times 1 is 2. 2 minus 1 is 1. So I am still going to get out the odd numbers with 2n minus 1. So now let's think about which one we might want to use to represent this particular set of odd numbers. Well, we do want to start out with 1, but notice that we have to start out by substituting in the index of 1. So if I start and I use this version of odd numbers, if I plug in 1 first, 1 times 2 is 2, plus 1 is 3. And that's the second denominator of my sequence. So I'm actually going to have to use this second version or way of representing odd numbers, 2n minus 1. So we should always test it out for a couple just to reassure ourselves. So if I substitute in 1, so a1 is going to be 1 over 2 times 1 minus 1. So that's 1 over 2 minus 1. So 1 over 1 gives me 1. Perfect, that works out. A sub 2. Well, I plug in a 2 for n now. And then 2 times 2 minus 1. So that's 2 over 4 minus 1. Or 2 over 3. That works. And this is the correct expression for the general term. So it will continue to work for the remainder of the terms that we have shown. So here, this tends to just be a little tricky because you have to recognize what the pattern is and how to obtain that pattern. So let's go ahead and do another example. We want to write an expression for the general term given this sequence: 1/2, 8 over 3, 27 over 4, 64 over 5, and so on and so on. So we have fractions again. I'll go ahead and start the index at 1 again. So this is going to be a1, a2, etc. So my sequence is a sub n, where n equals 1 to infinity. And my general term is going to be a fraction, as all of the numbers in the sequence are fractions. Let's start with the denominator because it looks a little bit easier, right? So 2, 3, 4, 5. So we increase by 1 every time, but this time we start at 2. So we can't just have n, right? If our index starts at 1, then that means our first denominator would be 1. We don't want it to be 1, we want it to be 2. So to fix that, let's just go ahead and add 1. So now when I substitute in 1, 1 plus 1 is 2. When I substitute in 2, 2 plus 1 will give me 3. 3 plus 1, 4, etc. So our denominator is pretty similar to our previous numerator, except for we want it to start at 2 instead of 1, so we're going to have to add 1 to every n. So now let's take a look at the numerator. So the numerator by itself as a list is 1, 8, 27, 64. So let's see if we can think about a pattern here. So 1 can really be written in so many different ways. So let's try 8, 27, and 64 and see if we can find some sort of pattern. So 8 can be written as 2 cubed, and 27 can be written as 3 cubed, and 64 can be written as 4 cubed. So now we can go back to 1 and see if it follows the pattern of 1 cubed, and it does. 1 cubed is 1. So what's happening in the numerator is I'm taking the integers starting with 1 and cubing them. So in other words, I'm going to want to replace 1, 2, 3, 4 with n. And my starting index is 1, so this is going to work out perfectly to be n cubed. So my general term for the second example is n cubed over n plus 1. Alright, so now we're going to briefly discuss the difference between a continuous and a discrete function, because a sequence is an example of a discrete function. And the difference is, let's think about f of x equals 1 over x. And the domain of this function is everything except 0. It's the only number I cannot substitute in on the entire real number line into this function. So the domain would be negative infinity to 0 and 0 to infinity. Those are all the things I can plug into x. Whereas the sequence a sub n, which we said we could think of as a of n, I can only substitute in the integers 1, 2, 3, 4, etc. into the n. I can't plug in 0, I will still get undefined. So those are the differences, but they're both still functions. Now let's think about that graphically. 1 over x is the reciprocal function, which goes through 1, 1, I missed that a little bit, and has horizontal and vertical asymptotes at 0, and then goes through negative 1, negative 1, and is defined over here in quadrant 3. So this is the graph of the reciprocal function 1 over x. Now let's think about trying to graph the sequence 1 over n. So let's write out a couple of terms. So a sub 1 would be 1 over 1, which would be 1. A sub 2, 1 over 2. A sub 3, 1 over 3. And this is a pretty easy pattern to see, 1 over 4, 1 over 5, etc. So let's think about these as coordinate points. So when I substituted in 1, I got out 1. When I substituted in 2, I got out a half, 3 a third, 4 a fourth, 5 1/5. And now we can graph these points. So the first point I can graph is right here at 1, 1. So that's one coordinate point. Then 2 a half, 3 a third, now it's going to get really hard, 4 a fourth, 5 a fifth, and then you can see that we're going to end up getting closer and closer to the x-axis. So I'm approaching the x-axis as my x values are getting bigger and bigger, or in this case my n values, the index, as the index goes to infinity, which hopefully you remember that the index is going to go to infinity because the sequence goes on and on forever to infinity. So what's happening to the numbers in the sequence is they're all getting closer and closer to 0. So hopefully that strikes you and that brings back to your mind the idea of a limit. So previously we thought about the idea of a continuous function having a limit. So as x values go to infinity, all of my y values get closer to 0. But it turns out that we can still extend this idea of a limit even when we only have individual points that are now getting closer to some value. In that last example, that value being 0. So it has a special name when we talk about sequences. It's called convergence of a sequence. So if the limit as n goes to infinity, so as we look out really far into this sequence, if all of those numbers in the sequence get close to some number L, then we say that the sequence a sub n converges to L. Otherwise, we say the sequence diverges. Alright, in these next examples, we're going to determine whether the following sequences converge or diverge. And these are actually pretty nice problems because we're going to be given the general term a sub n equals 1 over n squared, and the setup is always the same. To determine convergence of a sequence, we're going to find the limit as n approaches infinity of the general term, in this case 1 over n squared. So limits at infinity, remember, we can apply the rules for horizontal asymptotes to help us solve these limits. So since the degree of the denominator is bigger than the degree of the numerator, this limit equals 0. The denominator is growing faster than the numerator. Now 0 is a real number, so we can answer the original question. We haven't done that yet. The original question was whether or not a sub n converged. So a sub n converges, and more than that, a sub n converges to 0. We know where the values in the sequence are headed, where the numbers in the sequence are going to. They're heading towards 0. And a shorthand notational way to write that is a sub n, and we can write a little right arrow, 0. So now let's do the next example. We're going to set up the limit as n approaches infinity of n plus 2 over 2n plus 3. So just a quick warning, I know we're used to using x's, but when we're talking about sequences, we are going to have to make sure to use the correct variable, n. And so now, here again, the rules for horizontal asymptotes, the degrees here match. They're both 1. So we're going to take the leading coefficients, 1 over 2. So since this is a real number, a sub n converges to 1/2. So now 2 more examples. We're going to set up the limit as n approaches infinity of n squared plus 1 over n. So when the degree of the numerator is bigger than the degree of the denominator, we know that there's no horizontal asymptote because the function is either going towards positive or negative infinity. Well, in this case, if I'm plugging in big numbers and squaring them, it's going to make them even bigger and positive. And so the top is growing faster and it's positive, so we're going to head towards positive infinity. So here, infinity is not a number, so we can go ahead and conclude that a sub n diverges. And in this last example, we have the limit as n approaches infinity of n squared plus 1 over e to the n. So now here, we don't have 2 polynomials. I have a quadratic over an exponential. So exponentials, if you remember, grow faster towards infinity than any polynomial, including a quadratic. So if e to the n is growing bigger, faster than a quadratic, then this limit goes to 0, which is a real number, so a sub n converges to 0. Alright, we're going to conclude with some special limits that are worth memorizing, and some are a little intuitive and some are really, we have no other way of evaluating them, so that's why their answers are just given. So the limit as n approaches infinity of 1 plus 1 over n to the n is e. So this is definitely one that we're not going to be able to show why it is the way it is. It is just a given limit, that this limit equals e. The limit as n approaches infinity of the nth root of n equals 1. And the limit as n approaches infinity of x to the 1 over n equals 1. So this is sort of one we can talk about here because as n approaches infinity, n is this denominator in the exponent. So that means this exponent will go to 0 and anything to the 0 equals 1. And that same thing is happening here because you'll notice that this is n to the 1 over n. So if n is going to infinity, this exponent is going to be going to 0, and then any number to the 0 is 1. So that's where those are coming from. And then here, the limit as n approaches infinity of x to the n equals 0, but only if x is between negative 1 and 1. So some number between negative 1 and 1. Something like a fraction, like a half, or it doesn't necessarily have to be a rational number, but any number between negative 1 and 1 raised to the n is going to give me 0 as n values approach infinity. So these are just some special limits that often, not too often come up, but often enough where these are good to memorize.